Well, welcome to the 2014 Raymond Beverly Sackler lecture in the Raymond Beverly Sackler Lecture Theatre. And our speaker today is Sara Seager from MIT. She's a professor of planetary sciences and physics. Just a little background here, and that is she got her first degree in Toronto in the 90s, and then went to Harvard for a PhD, finishing in 99. Then she was a Keck Fellow at the Institute for Advanced Study in Princeton, a senior research staff member in Carnegie, and has been at MIT since 2007. The media picked up on her, and she's known as the astronomical Indiana Jones because she's searching for the holy grail of a true twin for the Earth. Time magazine made her one of the 25 most influential people in space in 2012. I don't know whether that means you were in space. And in 2013, she was being awarded a MacArthur Fellowship. Very nice. And my last comment is in 2012, she was the Raymond Beverly Sackler Prize. She received the Raymond Beverly Sackler Prize in the Physical Sciences. So it's very appropriate she give us her lecture for 2014 here. Thanks, Sarah.
Thanks, everyone. Thanks for coming out to my talk. I'd like to thank everyone for giving me a great welcome here, especially Director Andy Fabian. And I'd like to thank my host, Madhu, who many of you know was my first PhD student. I'm starting with this photograph, exposed photograph of a dark sky. Whenever I go to a dark sky, I look up at the stars, and I'm wondering actually if any of you get to go to a dark sky here. I'm not sure where you're, where your dark sky is. I know not everyone here is like an observational astronomer, but when I go out there, I look up and I wonder, are there planets around those stars with intelligent beings that actually may be looking at their sky back at our sun and wondering the same thing? And what's amazing now is that we know of thousands of planets. And we know, statistically speaking, thanks to microlensing, that every star in our Milky Way galaxy should have at least one planet. So I hope you do get to go to a dark sky here or somewhere else. And when you look up at the sky, you can actually wonder about those planetary systems around those stars. And to start off with, I want to show you this. I have made a movie from software that I hope everybody will go and download later for yourself or your you can pretend it's for like your friends or your kids or something. But actually, this movie will show us what we know about the stars around here and which ones have planets. This comes from a JPL software. It's called Eyes on Exoplanets. So here's what we think our Milky Way galaxy looks like. Those stars show you the stars with known planets. We're zooming in to where our sun is. And these local ones, these are all real stars with real positions in the sky around us. Here's our solar system, the outer planets. And you can see the inner planets also. If you look there, you'll see Spitzer and Kepler. They're in heliocentric Earth drift-away orbits, so they're also going around the sun. Now we'll zoom into Earth. This was made at JPL, so we're zooming in as if we were at Los Angeles and can see all the stars in the sky and the constellations. And now we're going to turn to look at the Kepler field, where the Kepler Space Telescope spent nearly 4 years looking. Look at all those stars there. All these highlighted stars have known planets. And when you download the software, you can search by name. This example is for Kepler 186f. Who here has heard of Kepler 186f? I know at least some of you have. It's going to zoom in and show us where that star is, Kepler 186f. And lo and behold, around that star, there are several planets, 5 planets. The system is about 500 light years away. It can tell us about the star, it's an M star. But overlaying here is the so-called habitable zone, where rocky planets heated by their star would be not too hot, not too cold, but just right for life. And when you click on it, it's funny here, because now it says hypothetical visualization of planet. It's called planet. Just so people using it who aren't, astronomers professionally know that we don't really know what these planets look like. This is just the artist's conception. So here we are. We know where all of our nearby stars are. And now we actually know where many planets are, thousands of them. This tells you here that on this version, they have 1,000 stars with planets here, but it's 1,767 planets. And the number is growing. So that was my sort of very fast, very brief introduction to the stars, and we know of planets. You can click on any of these if you download the software and just see what's out there, what kinds of stars and what kinds of planets are out there. So what I'll do now is return to some schematics of what is there instead of going through planet by planet, which would take quite a long time. So what I am going to talk about today is what we call it the search for Earth 2.0. It just means to search for other planets that might be like Earth. But it's quite a broad topic because it kind of depends how you define Earth and what you want to find now versus what's accessible half a century from now. And so I'm going to try to hit all of these main points through this list of topics. Okay, so I'm going to start by showing you a few summary slides, which I know some of you will be very familiar with and others of you won't have seen at all or have seen recently. And this particular example is showing you exoplanets by mass or minimum mass versus this is semi-major axis. It has a bit of a weird normalization here over the snow line, but for our purposes, just start out by noting that the axes are on a logarithmic scale. So it covers many orders of magnitude, going from planet mass. You can see the solar system planets, Venus and Earth, are at about 1 Earth mass and about 1 AU. You can see the other solar system planets. Now the colors, the colored symbols and the colors on the plot represent different planet finding techniques. And while I'm not going to address the planet finding techniques, I just wanted you to know that there's many techniques and that most of them are by today really quite successful and that they all occupy very different regions of parameter space. You can see that for the time being, so-called direct imaging can find planets very far from the star, and they're massive planets that also tend to be very bright. Now, about this diagram, though, if you look where Earth is, and remember it's a logarithmic scale, it's very hard to find an Earth analog, extremely challenging. And the parts of this diagram that remain dark is really for technological reasons. We have every reason to believe that this diagram should really be completely full. It should be full, although it may have clumps in places. But I like this plot because it not only gives us a snapshot of where we are in an exoplanet census, but actually for exoplanets, that anything is possible within the laws of physics and chemistry. Nearly any planet we could have conceived of in its orbit and so far its composition, it all appears to be out there due to a very stochastic process of planet formation. Okay, here's a similar plot, but now it's planet size compared to period. And planet radius is shown here. And let's see, I just realized let's see if I have a pointer here. I would hate to hit the wrong button that shuts everything off. Let's see if this is it. I'm not sure if I have a pointer because this is long.
On the
On this?
On the left-hand side.
On. Okay, I see. Right about that.
Press the button.
Right, okay. So this is better. Planet radius, so 1 Earth radius is here. 1 Jupiter radius, period in days, so our Earth would be about here. And this is all data from the Kepler Space Telescope. The one point I want you to see is just how many planets and planet candidates there are. This plot is just filled with planets. And not only that, I want to see if by eye, which kind of planet do you think is the most common based on Kepler data, ignoring systematics for a moment. I think you could probably guess. I'm not going to ask you to actually guess out loud, but are the most common type of planets Jupiter-sized planets? Are they something smaller? It's really amazing that not only Kepler, but other techniques have so far identified that the most common type of planet we know of in our galaxy actually is a small planet. We don't actually know how small yet because we haven't been able to gain robust statistics on the smallest planets. But if you look at this plot, it shows you planet size relative to Earth. So Jupiter would be here, Earth is here. And this is fraction of stars with planets a period less than 50 days. This plot now is complete out to longer, although people haven't published or really done the analysis. This corrects for systematics and the geometric effect of transits. And what you can see, I hope, quite clearly is that despite the error bars, if you just look at the histogram for small planets compared to large planets, is that small planets are far more common than big planets. And why I personally found this so shocking was the sort of traditional picture of planet formation is that a Jupiter would be the natural end product of planet formation. That as planets form and accrete rocks or rocks and icy material and grow to 10 Earth masses, it was believed that the planets would, in a runaway process, gravitationally capture everything around it in the planet's feeding zone. And so sort of natural, I don't know if it's a natural thinking or based just on one example, but I always thought that Jupiters would be just dominant and the most common object. So now it turns out that planets 2 to 3 times the size of Earth are common, very common, more common than a Jupiter. And this is a problem because we don't have a good idea of how they form. It's fair to say that in the field, imagine having the most common planet we know of so far, and we don't even know how it formed. So sometimes the question is, what would be the best problem to work on now if you were just starting out or wanted to work and solve a really hard problem? It might be this one. And that would be amazing to figure out how the small planets formed. But exoplanets, like other fields, but unlike other fields, we often run into a dead end based on like degeneracy in terms of you could have several reasons. And nature may form planets in all the ways we can think of and more. And so we may not have a unique solution many times in exoplanets, and so we may just have to live with some theories of how these planets might form. And so that's sort of TBD. But it's still a fresh field, and a lot is happening, a lot of data. This is one of my favorite examples. So at some level, there's only one thing to remember. I hope it could be this, that you could take away that the most common type of planet we know so far is 2 to 3 times the size of Earth. Hopefully they'll be smaller, but we don't know how those planets formed yet. So for the first part of my talk, I said, we know where the nearby stars are. You already know that part. We know that how common small planets are. I have to say, after my visit, I can't say that with certainty now, because apparently some of these numbers are being revised. There's different ways that we assess how common small planets are. And I just put up a couple of numbers here, but they may change actually. People think by extrapolation that Earth-sized planets in the so-called habitable zone could be 5 to 20%. It's kind of good. I mean, if you think about it, 1 in 5 stars may have a planet the size of Earth in their orbit. It may be less. So we're at least getting to the point where we can make some estimates, even if we have to extrapolate. Okay, so we know what kind of planet we're looking for. So in this case, I've sort of had this agenda, and I sort of say it a bit tongue-in-cheek, because everyone has a bit of a caveat. We know where the nearby stars are. We know that. We know how common small planets are, approximately. We know what kind of planet we're looking for. At least we kind of think we do. In this field, we still, like in all the fields, right, people always fight. So I'm going to tell you about one of the arguments that's going on right now. And this is about what kind of planet is a habitable planet. A lot of people, we want to go out and find an Earth. We want to try to find signs of life on another planet by way of biosignature gases that might be produced by life. But the question is, where do you look? What kind of planet could be habitable? We're very terracentric. We're self-centered, fixated on our own Earth. But if you think about it, the planet like Earth doesn't generate its own energy, not very much anyway. It has like radioactive decay in the interior and other sources, but it's minuscule. Earth is heated by the sun. The sun, star radiation that hits the top of the atmosphere, and it's our greenhouse atmosphere that controls our surface temperature. And you know how in the news, it's our atmosphere we're worried about. I just say you're going to probably laugh because we're astronomers, we might not be as worried as other people. But we're worried that parts per million of carbon dioxide. Right? But for an exoplanet, imagine if the planet is more massive than Earth and has a more massive atmosphere. Maybe it has twice as much carbon dioxide, maybe 100 times more, maybe more. Maybe it has such a massive atmosphere that it's so hot. And so when you think of the habitable zone now, it actually becomes a little different, given the diversity of planets. And the point I started with, that exoplanets are so diverse, we expect this to extend to their atmosphere. We don't know why Earth has the mass of the atmosphere it does. We don't really know. We know that it formed and outgassed and evolved and we had atmospheric escape, and then life arose and changed the composition. We know it was complicated, and actually people in Earth science fields, they try to work on the very detailed story, but it doesn't really help us understand the potential diversity. For me personally, I just assume it's very diverse. So we have this traditional picture of the habitable zone. Just for show, I was wondering how many people have seen this picture. Okay. I know if you took him out of his class, you would have seen something like this, but in this field, we have the habitable zone, and you can see the different star types here on the left. Sun-like star, M star, at half the mass of the sun, and could be at twice. And these are the planets of our solar system, radius 1 AU. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, etc. And the habitable zone changes. The closer the planet is to the star, or for a smaller star, M stars have lower luminosity output, and so the habitable zone is much closer to the star. Now, this is the picture that we had lived with for quite a long time. We have this, let's see. On the one side, it's water vapor. Venus, we think, most people believe Venus was born with oceans, but it had a runaway greenhouse process where the temperatures were so hot at the surface, the water evaporated. Ultraviolet radiation photodissociated the water vapor molecules, and the hydrogen escaped to space. And a runaway process happened that got rid of all of its water. On the outside, some of you may know Mars has carbon dioxide ice. It has polar caps made of water ice and carbon dioxide ice. Now, if your planet is too cold, the carbon dioxide freezes out. Carbon dioxide and water are the greenhouse gases. So without a greenhouse gas, your planet becomes too cold. And the surface temperature is too cold for life or liquid water or really anything that could support life. So that's the picture that we lived with for a while until we understood the diversity of exoplanets. And so now we have this revised habitable zone, and now this is the same type of plot, showing our sun. M stars, one that's down to 0.2 solar masses, showing you twice. These here are real planets in these points. Radius of orbit relative to Earth, so here's Earth at 1 Earth radius. And this cartoon diagram here, we made it based on the real model data, model simulations, right? So that's where the shape of those curves come from. And this blue band is what you saw before that has traditionally been around, and it's revised. Now what we see here is a very extended habitable zone. And I want to just address this briefly, partly to continue the theme of the diversity of exoplanets, but also to tell you sort of the latest in the field that people are trying to hash out. Now one idea is that we could have habitable planets much closer to their star than the Earth is to our sun, maybe half as close, 0.5 AU. And in this case, the concept by Andras Zom and a few others, Andras is a postdoc finishing up in my group, but the concept is that our own Earth, water vapor is our biggest greenhouse gas. We don't hear about it in the news because we're not adding more water or taking it away. The water cycle happens independently of us humans. But imagine we have a planet with less water ocean, less water vapor, lower relative humidity. That planet would avoid the runaway greenhouse, even being closer to the sun, because it's absorbing less, it's heated less, its whole greenhouse atmosphere is less. This has created a huge point of contention in the community. I don't know why people got so upset with the fact that we could have an Earth with less water vapor. There are actually specific technical reasons having to do with relative humidity, what is the lowest it could be, whether when a planet forms, it outgasses all of its volatiles and creates an ocean. Can you have an all or nothing situation, or could you have a tiny amount of water? But what I love about astronomy is that the observer, I don't want to say the observer's rule, because I know there are a lot of theorists here, but at the end of the day, I feel like our job is done here as modelers, and we'll wait. I'm looking straight at what are the observers here, and I'll look at an observer. We hope that with the next generation, you can find planets at the equivalent of 0.5 AU, depending on their star type, right? And you can look at their atmospheres and see if they have water vapor or not. So we'll see. So anyway, we send a habitable zone, but I think for the general astronomer purpose, I think the outer habitable zone is even more interesting. Now we're imagining planets that we know exist, super Earths, more massive than Earth. And I want you to imagine a planet that's more massive and colder. And having a massive atmosphere with a massive greenhouse effect, such a planet may be habitable further out. But there's a twist here, and it has to do with molecular hydrogen. Our own planet Earth, we don't have hydrogen or helium. Those gases are too light for our planet. But a planet that's more massive or colder, we expect it will be able to maintain its hydrogen. And again, I don't feel like I have to defend this. Our own Earth had hydrogen outgassed early on. We see it in the record, geological record, isotopes and other things. We just don't know how much or how long it lasted. And again, observations will tell in the future. So imagine now a planet with molecular hydrogen. Well, I bet there's at least some people here who work on white dwarfs. And you people know about collision-induced opacities with molecular hydrogen. Because hydrogen, unlike other molecules, hydrogen is homonuclear. And it doesn't have discrete rotational vibrational bands, like water, methane, and other things. They have discrete bands, or even atoms, right, where they absorb. But hydrogen, it gets an induced dipole moment. And depending on the energy involved in the collision that induces that moment, it actually has a continuous absorption, as long as the pressure is high enough to have these collisions. So imagine what happens now if you have a continuous absorption spectrum. Instead of having discrete ones, you actually have a much stronger greenhouse effect. H2 is a nasty greenhouse gas. If we had it here, we'd be a lot more worried. Well, we probably wouldn't be worried because it would be saturated in a way, but it's such a strong greenhouse gas that if it is there, the planets with molecular hydrogen would be habitable much further out because of the power of the absorption power. And I'll just summarize in this. This was an invited review article, invited to be provocative, to put things together in a big way. And it wasn't provocative so much out here. The people who wrote that paper, Ray Pierre Humpert at Chicago and Eric Gaidos, and they argued that you could have a planet as far out as, I think they said, a 2 Earth mass planet in 10 AU or something. It was quite far. And people have even postulated that you could have a free-floating planet that was ejected from its system with the right hydrogen atmosphere and the right amount of radioactive decay on the inside. But for what it's worth, we don't know yet. We just think the picture is so vast and revised now that it's a rich possibility. And one more thing about hydrogen, unlike carbon dioxide, it doesn't freeze out at warm temperatures. It can go to 70 Kelvin before it condenses out. So I'm personally very excited about the potential of planets with hydrogen atmospheres, and I'll get back to that. So I say we know what kind of planet we're looking for when we're looking for Earth 2.0, but actually that's kind of only approximate. We want a planet's surface temperature that could have liquid water. Water is needed for all life that we know, but more importantly, we want the surface temperature to be, not too hot or not too cold. If it's too hot, we can't have molecules. We'll just have atoms. We need molecules so we can have complicated things and have life. So we want the right type of planet with the right surface temperature. But given that we don't understand the range of atmospheres and compositions and greenhouse effects, we're kind of on hold a bit. We have this sort of vast concept of what could be habitable, and we need future observations to help us narrow down. So, okay, this topic here gets a little more detailed. We kind of know how to identify a planet like Earth. And here, what I want you to know is that we have, when we think about Earth from space, some people, you think of the beautiful Apollo images of Earth. We're not planning, already know this, right? We're not planning to see anything like that anytime, at least in the near future. What we want to see is this. This is also a real photograph of Earth. And this is Earth as a pale blue dot. Can you see the 1 pixel Earth on here? It's taken by the Voyager 1 spacecraft at 4 billion miles away. And this picture here is so representative in my mind because you see this pink line here. It actually is scattered light in the camera optics. But what it really looks to me like is zodiacal dust. When we imagine looking at our planet from far away or looking for an Earth around another star, our dust belt, our zodiacal dust, our asteroids collide and they make dust, and the dust reflects in the red. And we have to try to be able to resolve the planet above the zodiacal dust when the time comes to do this direct image. So people have studied, you would not believe it, Earth as an exoplanet. People use spectra from spacecraft that are made to look back at Earth. And I have one example to show you here, just so you have an idea of what we're looking for in the future. This is showing you relative brightness, and this is wavelength. It's kind of awkward here. I think this is in angstroms, actually. So this would be 1 micron here. This is visible wavelengths. And this is the near infrared here. So 1 micron, 2 microns, 2.5 microns. And actually what you're seeing here, if you want to go for the spectrum, you're seeing a lot of, let's see, he hasn't marked water vapor. Most of these are water vapor features, and he's showing you some smaller features here. You know what this is? I want to tell you how this is done. This is a very clever experiment. One of them is actually from Earthshine. When you see the moon, it's showing you here in case you, for some reason, haven't noticed this phenomenon. You see the Earth. If you go up and look at the moon, have you seen this when the Earth is a crescent moon and the other part of the Earth looks lit up? That is actually light from the sun that hits the Earth, and then it reflects off the moon and comes back to Earth. And because the moon is an imperfect reflector, it's so jagged and it's not a mirror or anything. So what you get back, if you look at part of the lit up part of the moon, the so-called Earthshine, is you actually see the Earth spectrum spatially unresolved. It's like having a very blurry mirror, actually. And so people did for a while, it was very kind of in vogue to take spectrum of Earthshine. You have to calibrate it because you look at the bright part of the moon where you get the reflected sunlight, and that other part where you get reflected Earthlight, and you get to subtract the part of Earth's atmosphere and see how it looks. So this is how it would look in reflected light. Well, it would be mean of me to ask you to guess which was reflected light. But okay, so one of these is reflected. You see Rayleigh scattering, and you see a bunch of other features. And now Henri Palais, he's in Tenerife at IAC. He did something very clever, and he also looked at a transmission spectrum of the Earth. This is more challenging to think. This is a bit of an aside to the whole talk, but it's amazing to be able to study Earth as an exoplanet. And what he did was, I'll just tell you briefly, but you might have to go away and think about it. It's a few times, once in a while someone will do something like it. I wish I thought of that. It was so clever, but he looked at transmission during an eclipse, a lunar eclipse, when the Earth basically blocked the moon. So sunlight went through Earth's atmosphere, hit the moon, and then came back to Earth. Got to think about that for a moment. I know that someone's smiling, because the big argument I had was, I think refraction plays a role here. You would never have this happen, because otherwise the sun's rays would go through Earth, right, and they'd never hit the moon and come back to Earth. And in their paper, they ended up ignoring refraction. I don't know if it was mine or not. But the point is, if you wanted to care about reflection versus transmission, there's a lot of hidden information in here. Namely, you can see that in transmission, scattering is, remember how scattering can be like absorption, so it gets removed from the beam. You can see the transmission features are often deeper than the reflected light features because of the very long path length through the atmosphere. But anyway, for what it's worth, if you didn't get a lot of those details, we try to understand Earth as an exoplanet. And in the future, we'd like to get real spectra like this of real rocky planets. But for now, we're very far off. We don't have any planets that might be anything like Earth that we could get a spectrum of right now. We're very far from that. And I'll come back to that at the end of my talk. For now, I just wanted to give you a very brief tour de force of where we are at with exoplanet atmospheres. And that's where the kind of cartoon diagram is sort of in lieu of the whole detailed tutorial of models was supposed to help you understand the challenges we face here. I want you to think about it, especially if you work on spectra of stars or white dwarfs, or if you're looking at galaxies. what the problems we have to face. We have a planet, and it's a very dynamic environment because it's not like a giant planet or a star that maintains all the gases it's born with. Stuff's happening. And here in this cartoon, we show that we have volcanoes or flux coming out of the surface. Life is producing things. And then the chemicals mix in the atmosphere. And after they mix in the atmosphere, they're actually photochemically altered by their star. And so whatever goes on, you sort of have to, each one of these would be like a PhD thesis. But the field evolves rapidly, so each time you kind of need a continuous person working to understand photochemistry or geophysics connection to the atmosphere. And here I've shown a concept of the space telescope, trying to look what's going on. We also have atmospheric escape. Many mechanisms can do atmospheric escape, and we don't have a great handle on it. But I actually only have one slide for the model, just in case anyone here didn't know anything about exoplanet atmospheres and wanted to know. To know more, I'll point you to Madhu, and also Kevin hangs here for a while. But essentially, in a very simplistic way, I look at it as having, here I've shown, sort of 6 sets of equations and 6 unknowns, essentially. And many of these you'll have seen before. We have just energy transport. I've just put rate of transfer here. We have conservation of energy in each layer because the atmosphere doesn't produce any energy, just energy gets transmitted. We have hydrostatic equilibrium. The ideal gas law, thankfully, holds. And then we also have a series of equations to describe chemical equilibrium. And this kind of depends on how you want to do it. If you want to do photochemistry, you can have like hundreds and hundreds of equations with different rates and time constants. Sometimes they're not even really known that well. Then you put all of this together, and you want to drive flux and temperature and pressure for each layer, also density, and the chemical composition of each layer. I just show this to you so you can maybe orient yourself of where we're at. We have a systems of equation, a systems of unknown, and sort of it makes a nice problem in a way, but what we're faced with is just a ton of uncertainties. Most things for our inputs we actually don't know. We don't know what they are. The only thing we could say we know for sure in advance of observations of the atmosphere are the surface gravity of the planet, if we know the mass and size of the planet, and the radiation from the star. And that can be all we know. We actually have a lot of complications. I won't go through this actually in the interest of time. I wanted you just to know that it's all thought of in a lot of detail. And we actually have everyone's working on all these problems trying to know what's going on. So instead what I'd like to do is take you to some real data and tell you what the highlights in the field of exoplanet atmospheres are right now. And partly how it relates to Earth 2.0 is I just want you to know we're getting ready. This is like science in and of itself, but at the same time like a test case. We work on the giant planets, which we think maintain all the gases that they're born with. Should be hopefully easier than thinking of exoplanets. And the way that we study planets today with atmospheres is primarily by the transit method. When the planet goes in front of the star, some of the starlight shines through the optically thin part of the atmosphere. And we can actually pick up the light from the exoplanet atmosphere. I see all of you just kind of looking like, okay, this is all okay, but I just want you to know when I used to first start talking about this, I was like the first person who actually ever worked on this. And people were just dumbfounded. They're like, this is never going to happen. We're never going to have enough transiting planets. And so I just want to impress upon you how amazing it is. Like, you'd be here today, and you're like, okay, I already kind of either know about this, or it sounds pretty standard. And it's really just a decade old that we even have this. We borrow heavily from binary stars, so this kind of thing had been done before, but not for planets. So here you see there's more details to the technique, and I'll refer you to Brief's demo right here to get the ins and outs of all the systematics and how hard it is to actually make the measurements. So what I'm showing you now is one of our showcase planets, HD 189733b. It has about a few day orbit around a K-star. And someone can correct me if I'm wrong, I may be off a little bit on the exact parameters, but it's a kind of a Jupiter-sized, Jupiter-mass planet. It's hot. It's in a very short period orbit. Orbits many times closer to its star than Mercury does to our sun. We think it's heated to like 1500 Kelvin. Okay, so it's hot. It's not like, more like a brown dwarf really than what you might think of as a planet. And what this is showing you is, I didn't explain exactly how the technique works. So what happens essentially is if you imagine light from the star going through the planet atmosphere, at wavelengths where the atmosphere is strongly absorbing, the planet actually is a little bit bigger. And, if it's opaque to some wavelength, it'll look bigger. If it doesn't absorb, it looks smaller. But for what it's worth, you can also just think of this as a planet spectrum. It just says radius ratio for that reason, but you can also think this as a kind of like level of intensity or flux. Now here's wavelength in angstrom, so this is 1 micron. This is visible wavelengths, and this is the infrared. These points are taken with Spitzer. These are Hubble Space Telescope data. Now I want you to look at the model, the gray model. Okay? And the data are the black points with their error bars. And I'm sure you can see how the data does not agree with the model. Right? No one's claiming that it is, but I just want you to take a good look at this because the model was made to illustrate what happens for a case when there are no clouds on the planet. If you're assuming it didn't have a cloud, it's still hot planet. It doesn't have water clouds. And now you can see the data show that essentially we think what's going on, and we meaning the community here, that this planet has a lot of clouds. It has clouds or haze or some kind of particle blanketing out the atmosphere. It's like when you go on an airplane and you fly through the cloud, then when you're looking down, you don't see the atmosphere, right? You don't see anything. And it's actually, atmosphere is exponential in density and pressure. So if you block out with clouds that atmosphere where all the lines would form, you really don't see too much. Actually, we think that's what's happening. That clouds have maybe ruined the experiment, if you will, because we're unable to see. Look at this point here. If you believe this, it thinks it's showing you this strong absorption feature of an alkali metal, sodium, showing you that. So that might believe, but it's not Rayleigh scattering in our atmosphere. Where honestly, it would go up like that. So it's a different slope, but it's reminiscent of Rayleigh scattering. So we think that's what's going on here. So the good news is we have great data. What we call great data for this field of exoplanets. And we have about maybe 5 planets where we have transmission spectra data that look this great. And so it's good to get data now, but great data and brings new questions. So this planet has clouds, that's for sure. We have another planet. Let's see, just trying to think of how much detail to go in here. I think for now, just for time, I'll just jump to this data. This planet is GJ1214b. It's a planet that is it's a so-called super Earth or mini Neptune in a short period orbit around an M star. And before, actually, no, I think I will just show this to you. So this was originally in this field. What we're doing is we're using instruments that were never intended to be used for this type of measurement. So people, I'm sure that many of you have been in this situation where you're pushing the frontier. And you have kind of two sigma data. It looks like there's something there, and you get very excited. But you've pushed it, and it may not be real. And here you're seeing like a spectrum of this planet, GJ1214b. And I just wanted you to look at this data here from the Hubble Space Telescope and the models. We're trying to see which situation is valid. Do we have, my favorite atmosphere, the hydrogen, the puffy atmosphere. Hydrogen is very puffy, it has a low molecular weight, it's an extensive atmosphere. You can see big spectral features in transmission because there's a large annulus being projected on that star. Or do you not have a pure hydrogen atmosphere, clear hydrogen atmosphere? But instead you either have clouds or you have a high metallicity atmosphere. So in this case, clearly it rules out. The planet does not have a big hydrogen atmosphere. It's ruled out, unless it's a very cloudy one. But I want you to look at this for a moment. This is sort of, you would not believe how many people agonized over this. Do you think you see a little rise here that might mimic this blue line, which is a watered down version of this water feature? You see, it's sort of funny, right? I'm sure you've all had, yeah, sort of, right? What would you do with this? Well, we've seen this so many times. I'm sure whatever field you're in, if you're at the frontiers of data. Well, I've seen this many times, maybe 10 different times. I've seen something that's, wow, it's not enough to know. It was probably nothing, unfortunately, but it was enough to do a proposal to get as much Hubble time as needed to actually resolve this. So the question is, if we get more Hubble time, and it was many transits were been together, 10 transits. This was very helpful in recognizing that we need 10 transits, not just one transit observation, but 10 of them, and bin them together and see what's going on. We did have a lot of hope for this planet, and in the end, look what we see. I was part of this, but it was led by Jacob Bean and his graduate student, Laura Clydeberg at the University of Chicago. This is showing you the spectrum here, going from 1 micron, 2 micron, 3 micron. This is a new camera, Hubble Space Telescope Wide Field Camera 3. It is zooming in to show you the new data here. So the old data is this gray, hoping to see this little water feature. And look here, basically a straight line. So all that Hubble Space Telescope data showing no, it's a straight line. And so that's kind of a problem, right? Because we want to sort of know what's in the planet atmosphere, so they're all very new to us. We understand theory now, we have complicated models, we want to see what's going on, and there's clouds there. Same for this other planet, GJ436. The data is just showing you a straight line. I know it sounds kind of depressing, but I could walk you through it. Here's one, HG29458b, with that same camera at this one special water vapor feature, and they do see a water vapor feature here. And by the way, this is showing you just 2 different models, but I wanted to just mention that the field has really progressed rapidly. The sort of our e-folding time for new ways of doing things is just a few short years. And I just wanted to mention Madhu. I think it may be fair, I don't know how to say this without embarrassing him, but we basically kind of invented this field of atmospheric retrieval for exoplanets, borrowing heavily from solar system science. We used to call it the Millian model approach, because the equations I showed you, you can't write down the matrix, like with the equations and with the data and then invert. There's no inversion. You can't invert it. You have to kind of do like a million forward models and then try to extract it. The community now since has developed Bayesian models and other things to sort of retrieve data. So when we have a great data set, we don't just make a couple models and fit it. We try to do a true retrieval in terms of trying to tell you the abundances of different molecules where we can, and essentially the limits of how well we can constrain them. So there's that. But just to summarize for you here, this field is moving forward rapidly. We're very excited about that we have atmospheric data to talk about, and we're not sure what's going on with these clouds. Every planet in our solar system has clouds of one kind or another, and it's looking like it might actually be true for exoplanets. It's a bit of a puzzle because they're so hot, they don't have water clouds. And this is put together by Andreas Sohm, and he's showing you number of planets for which we could say whether we think they have clouds or not. A few may look cloud-free, at least as far as we can tell, but most of them appear to have some kind of clouds one way or the other. And so that's kind of where we're at. We don't totally understand cloud formation in general, but we have great spectrum. We know that a lot of them are looking cloudy. So if you have any questions on atmospheres after I leave, you can talk to Matt and he can help you sort through it. So for this part of my talk, I wanted to say, we think we know how to identify a planet like Earth. We want to look at the spectra, but our lessons learned are that spectra are very diverse, including that atmospheric clouds may be a limiting factor in the future. So that's where we're at for that. Now I get to the last part of my talk, which is my favorite part. And I'm getting to tell you what I've been working on pretty much most of my time in the last 18 months. We're developing the required space telescopes. Now we actually have this two-pronged approach in the community. And the one prong is what's going on now. That's how we're going to find ground-based and space-based use assets that we have already. I'm talking about KOPS. I hope you all, KOPS and TESS is, in America we have a Transient Extrasolar Planet Survey satellite. Ground-based efforts like Speculos and GTS are trying to find a pool of planets. And we're going to use the James Webb Space Telescope to look at their atmospheres. So I hope that I or someone else can come back here in like 5 or 10 years from now, and instead of showing you these hot Jupiters, they can show you spectra, transmission spectra of rocky exoplanets going in front of them stars. That whole field is going to flourish right in front of us. But what I'm here to tell you about is something you might not have heard about, and that's the bottom one, the future Earth-like planets orbiting Sun-like stars, which will require new technology. So the problem we have is that with transiting planets, which most of what I've talked about, the transmission spectra, all those planets from Kepler, that transits are only the first part of a long story because they have to be fortuitously aligned. You know that all stars, when they form, it's like a collapse of a spherical cloud, so we think the rotation axis of the star, it's randomly oriented with respect to us. Planets appear to orbit in their star's equator, some don't, but whatever reason, they're all random. So transits are just the ones that are just aligned properly. So that it only takes us so far if we want to know about the planets around the nearest stars. And if we want enough photons, we need nearby stars that are also bright to be able to study their atmospheres and their reflected light. So the problem we face, actually, it's not that an Earth around a nearby star is so faint. It's not fainter. I always used to say that. I have to change that now. It is about as faint as the faintest galaxies ever observed by Hubble. Okay, so Earth itself, it's not so ultra faint, right? The problem is it's right next to a very bright star, its sun. And our sun actually is 10 billion times brighter than our planet Earth. So to be able to study the nearby stars for Earth, we want to block out the starlight, suppress the starlight to 1 part in 10 billion. And what I do whenever I get to talk to a technical audience, I say, well, have any of you had to work at the level of making a measurement or doing something at 1 part in 10 billion? Actually, sometimes there's someone who says yes. You know what it is? It's the people who work on gravity. They work on Einstein's theory. They try to test the gravity. So occasionally somebody says yes, but on the whole, it's like, no, why would you? Why would you ever have a reason to measure something to 10 decimal places or to suppress data? It's almost insane to even consider this. But actually, this activity has been going on a very long time. So we have to do the so-called direct imaging approach. This is just a cartoon to tell you what we'd like to do is put up a giant screen in space and block out the starlight so we can see the planet directly. The problem we have that is diffraction, right? So this is the top cartoon is showing you if you have like a perfect telescope in space, or if we put a giant screen in space, we have an internal coronagraph, and if it's a circle, we will measure this area ring pattern because light is acting like a wave. But let's imagine for a moment you could make a different shape to your primary mirror, or you have an internal coronagraph, or the giant occulting screen, it's a different shape. If it's a shape of like this star shape, your image will look this way. And if you make this shape precise enough in terms of the width of the petals, and we call this the star shade. It's like looks like a flower, so we call these petals. If you can make this precise enough, you can get this whole central region dark enough to 1 part in 10 billion. And people have been working on many ways to do this, internal to the telescope or external. And the analogy I give to the public, I just want to try it on you because it sort of hits home with how remarkable this idea is. But it's like dropping a pebble in a pond. And instead of getting the ripples, all around the pebble would be so perfectly smooth to 1 part in 10 billion. But out at the edges are where all the waves would be. So this is an amazing idea, and I can't take any credit for it. But what I am doing right now is I'm leading this 18-month NASA-sponsored study for how to build a star shape. Can we do anything? These 2 missions, internal and external. I just put this up so you can know that there's serious effort going on, and you can look at these reports. We're working on our final report now. We actually have a real design team at JPL. We're being costed by an independent review company. For those in the know, it's aerospace. And I just want to share with you for a few minutes some details of the star shape, so I could leave you with something, a new big idea. But just in sort of a basic technical overview, is showing you a picture of a telescope and a star shade, and it's supposed to show the distances. This star shade would be tens of meters in diameter. It has to fly tens of thousands of kilometers from the telescope. The good news is that the star shade does all the hard work. So when you learn about how the telescope aperture does your resolution, lambda over d, don't forget about that. You have a small telescope and achieve a much greater angular resolution on the sky, because if the star shade is made properly, you're transferring all the hard work to the star shade. So we imagine a co-launch with a telescope. It could basically be studied like a commercial Earth observer. You just get a copy of that was already made, launch it, fly away from Earth's gravity, either at L2 or in a heliocentric driftway orbit. Let's see, this gives you some information, but the one thing I put this here to remind myself is that the idea came up in 1962 by Spitzer, and every decade it was worked on again, 74, 85, it came up again in the year 2000, and it was sort of reinvigorated by Webster Cash in about the mid-2000s. And just the biggest challenge for the star shade is it has to retarget to each a different star. And so in the team, we have to think very carefully, if and when we actually do this project, you could look at one star, but you have to carefully move across the sky. So you have to choose your targets very carefully. And you have limited fuel, so you may have, let's say, 30 to 50 maneuvers a year. And basically you have a limited maneuvering time. But depending on your telescope and your other instrumentation, you could honestly get the equivalent of a Hubble Deep Field for every observation and discovery of a planet. You could equivalently be looking at a part of the adjacent sky in a lot of depth. So this was just showing you ecliptic latitude and longitude. I didn't want you to study in any detail. It was just to address that point. But now I'm going to, I just have a few more slides showing you a few movies. This is the concept where the star shade and telescope would launch together, and the petals would unfurl from a stowed position. There's a central truss, a central hub there that would expand. The spacecraft is in the center, by the way, and those petals would have a second stage of deployment where they completely unfold. Now this star shade would have to fly very far from the telescope, mostly because of diffraction. They have to create the right shadow of the right depth. Now there is a bit of play there, but not as much as you would expect. And that star shade would go very far away and miraculously, block out the light, and you could see a few planets. So that's the animation. You can look this up. It's been shown around quite a lot. But an even better movie, honestly, is the real deployment test from about a year ago. And this movie comes from Northrop Grumman and Princeton. It's in Northrop Grumman. And this is showing you 4 prototype petals made of flight-like materials. And they unfurl. There are longerons there. It's hard to see, but they are going to snap into place, rigidizing the petals. That truss, it's a little bit too tall. It is left over from large radio deployables made by Northrop Grumman. They've put large radio communications dishes in space. Now you can see the petals unfurling. Now the second stage of deployment, remember from the movie where the central truss expands and the petals snap into place. I always get asked why are there people in this movie. It's because not because they're supposed to automatically deploy. They want to show that in deploying many times over that the petals will go relative to each other within a few millimeters to meet the tolerances required to make the right shape. So they did this test 25 times, and I actually have one of these petals in my office now, and it fits in my. I have them cut it out into 4 pieces, and unfortunately I can't bring it out of the country in America, but it's on loan to me from JPL, and I do take it around to different places. You'd be everyone from the NASA administrator himself to like a 10-year-old child, everyone in between. They come up and they touch the petal, they lift it. And the funny thing was, it has these. When you take a picture of it, it's got these very bright reflective dots. And those are for metrology, because how do you measure something to within millimeters with respect to the other petals? The petals are constructed and you have to measure the shapes. That's all done at JPL. And so just 1 year later, here's another picture. Now look at this truss, it's much shorter. They designed one that's really at JPL over the summer. They had 12 summer interns. This one's only a half scale, the other one was mostly full scale. And here they have shown this one deploys automatically, actually. They have to have gravity offloaders. But there's quite a lot of work going on in this field, and I'm just trying to think of, I don't have too much more time because I wanted to leave time for Q&A. But I'll just say one more thing, actually. I can't go through all these plots here, but I want to say that the way that we try to convince ourselves and then the community is by precision manufacturing and measuring that the petal and that the prototype star shade can be made and deployed to the right position. So showing that it can be done on the full scale. And secondarily, we have to show that the math works as we expect, that if you make a star shade, you can try to get the contrast required, the 1 part in 10 billion. And so people do it in the lab on the 0.1% scale, like this, a star shade this big in a lab in a very long distance to show if they can reach, get the right pattern that's expected. And a sort of more fun way that's been going on, actually much more tedious and hard work though, is in the desert, because you need a very long distance if you want to scale this all down. The star shade is about 1 meter. I actually used to also have one of those. They needed it back for the desert testing though, but it's like about this big, and the edges of that petal are very sharp, like for mathematical reasons and getting the right diffraction. There's various solutions, but it's so sharp that if I took it around, it would really hurt. It would hurt you. Like, even if you have like the tightest sleeve woven clothes, it would pick out a little thread. So there's the star shade. It's about 1 meter across, and they go to the desert every spring and fall. And here you can see this is a 3 kilometer distance. The star shade is in the middle here. You can't see it, but they have like an LED bank with a fake, star and then fake planets of different distances and luminosity, kind of luminosities. And here's just a nice picture of what really happened. And they actually end up with pictures like this. They try to see what they can get to, and they actually make star shades that end up having. This is a planet LED at 10 to the minus 8, 10 to the minus 5. So they're working to get to better contrast. And they also make star shades with no defects, so they can see that it behaves like their modeling says it can. Okay, so we're developing the required space technology. I said that this decade we have TESS and GTS, Speculos, and Chaos to discover planets orbiting M stars, and we'll follow those up with the James Webb Space Telescope. We'll look at the atmospheres. We'll look for rocky planets. We'll try to see if we have these hydrogen-rich planets. We'll look for planets that are more like Earth's atmosphere if we can. That'll be very challenging, but look for carbon dioxide. And if we're really lucky, we may have a shot at finding some biosignature gases there. We're more likely going to have to wait for direct imaging from space to block out the starlight to see the planet directly. So I just have a couple of more slides to summarize the search for Earth 2.0. I wanted to give you an overview to bring you kind of up to speed of where we're at. We know where the nearby stars are. We know that small planets are out there. We're trying to figure out how common they are. We understand there's a wide range of planets that could be habitable, and this kind of increases our shot at finding a planet that may have signs of life. We're learning a lot about atmospheric spectra for exoplanets. We've got data now, and we're working hard to understand what's going on. We've developed a lot of theory, and now we have data to interpret. And finally, I mentioned how we are developing the required space telescopes. So now I wanted to leave you with a thought that it may be a little extreme for you, but I thought you might enjoy it as something to think about here. And that is about exoplanets. And we actually, we often don't talk about this out loud, but I thought I would take the opportunity to say it to you that, we think of this exercise in a way as a map-making exercise. We've mapped the stars, we know where the nearby stars are, and now we're looking for the planets around those stars. And I just wanted to share with you something that I've been mulling over lately. I think about my ancestors from 100 years ago. They actually left the Ukraine of all places, but wherever it was, they left like a poverty-stricken existence, and they took a deep breath and they went across the ocean on like a dangerous voyage to the New World, where they started a new life. And I think about them because I never met them. They were my great-grandparents, but all the thing they knew for sure was that it was a one-way trip, and they were saying goodbye to their family they never saw again. But them going there, I think it was a huge deal. Many people did that. And then I think about 1,000 years in the future, where I do believe, and here you're welcome to challenge me, but the good thing is that so far in the future, none of us have used the light. We have this human drive to explore. We left Africa, and we have this drive to always continually explore and to go to new places. And I believe that someday, I like to think it's 1,000 years from now, that we will be going. Our descendants, actually, will find a way to travel to those nearby stars. And when I think about that, it's not really just me, right? It's like all of science. But we're thinking, how's this going to happen? Are we going to hibernate? Are we going to be in multi-generational ships? More likely, you know what, now that our colleagues in like bio, you know, they print heart cells in a petri dish. Some of you know about this. 3D livers are being printed. We'll probably just send our information. But however it is, I am convinced that someday it'll go there. And that those people will look back at us collectively. It's all of us here who are here being astronomers, studying stars and our galaxy and planets. And they will remember us here this time when those first Earth-like worlds were found. Thank you.